it's a 4 in case you couldn't tell. There's no plus c because there's no constant, right? Yes? No? Yeah? So first we have x equals 0. So if x is less than 0, if x is -1, what's the sign here? Gonna be negative, right?
Yeah.
And then if x is +1, it's gonna be positive.
Yeah.
So decreasing and then increasing tells us that 0 is a local min. So we have a local min at the point 0, 0. Love those straight up polynomial functions, right?
Yeah.
Okay, so let's look at the second derivative. So taking our first derivative, it's going to be 12x squared. So the same, we have an important point at 0. When x is negative, what's the sign? Shukai?
Positive.
When x is positive, what's the sign? Michael?
Positive.
All right, so our special case. So what does this tell us about point 0?
It's just
Yeah. So what is it not? So what would we say about this function in general?
it's not a point of inflection.
It's not a point of inflection. So does this graph have a point of inflection?
No.
No.
So what does that tell you about the graph? The concavity does not change. What is the concavity, Michael? Correct. Right? So basically what this means is that it's just positive, it's concave up for the whole thing, so there is no concavity change. So we still know that the graph is concave up. We're going to have our endpoints pointing to positive infinity, but 0 is just a local min. So because there is no sign change, it is not a point of inflection. Everybody cool with that? I think we've talked about that quite a bit, so we're good there. I'm going to skip this one, given that we spent so much time on one that was much more challenging with the same idea. It's going to have the same, because we're looking at an x to the 1/3, it's going to have the same patterns here as what we saw over here with restricting the domain. All right, so this is one of two things that we need to do. So this is going to be challenging for me. So before we begin, the point of clarification that I really needed from Mrs. Leathhead in prepping was to talk about velocity and acceleration and how they work. So based on what you've already done in class.
I think we all got these ones.
Oh, did you all?
Yeah. Because the velocity is just the derivative function, and acceleration is just the second derivative.
That's
and then
easy for me.
Find the motion, you just have to graph it.
Easy enough? Okay, perfect. Then we will skip that. Thank you, Spencer. All right, so the second derivative test for local extrema. So this essentially combines the two theorems that we worked with earlier. So the first theorem was just with response to the first derivative and says, if the first derivative is, if the function is, you know what I mean. It said about the first derivative gives you local min and max.
Oh yeah.
Right? So this one combines the two and says, instead of doing your sign analysis for this separately, you can skip the sign analysis for the first derivative and use the sign analysis from the second derivative to tell you if it's a min or max. So this is a shortcut theorem.
Yep. Yeah,
Okay.
This is like problem 33 to 38.
Okay. So if you open up your homework to 33 or 38, as you go through, check to see, did you do it using the sign, did you do a sign analysis for the first derivative and the second derivative, or can we apply this to make it faster? So if we look at this, the derivative of this is going to be 5x to the fourth minus 80 plus c. When we set it equal to 0, we can take out a 5, and that gives us x to the fourth minus 16. What does x to the fourth minus 16 factor to?
X squared plus 4.
X squared minus 4.
This is going to give us imaginary values, since our domain is the real numbers.
And can we factor down x squared minus 4?
Yeah.
We sure can.
X plus 2, x minus 2.
So our, so these are our critical points, but now instead of just doing the sign analysis, we can go right on, especially given that this is a polynomial. We're working with 5x to the fourth minus 80. We're going to be able to generate that second derivative really quickly. So that second derivative is just going to be 20x cubed minus 80. So we can,
Wait, should it be
20x cubed.
Yeah.
Okay, so x is equal to 0 at 0. Okay, so now let's do our sign analysis for 0. So if x is less than 0, 20x cubed is going to be, if x is greater than 0, 20x cubed is going to be. So now we can go back and evaluate these 2 points. So at the point x equals positive 2, what's true about the second derivative?
Positive.
Positive. So that makes this a local min. At x equals negative 2, the second derivative is negative, so this is a local min. So this is especially useful if you're doing like a non-calculator portion of a test, because what you notice is if you had to take these and continue to plug them in here to do your sign analysis, that's going to give you some pretty big numbers potentially. Same thing here. So this is kind of a shortcut past continuing to plug these in, or if you have a lot of different critical points along that. Okay, so we could say that there's a local min at 2 and a local max at x equals negative 2. Is everyone cool with that? So when you look at the problems that you did for homework, did you use that theorem to do the homework, or did you?
Yes. Yeah.
Yes, yes, yes. You found it in your book. How about you, Michael? Okay, well, perfect. And now you can know to do it before. That's no worries. Your homework wasn't due today, but now you can use this theorem when you get to those problems over the weekend. Okay? All right. So go ahead and do this one using any strategy you want. So if you want to use the theorem we just used to define this, and you can, that's just great. So go ahead and do this right now. What do you need to note about the function here?
It's a derivative, not just that.
Okay. So let's see how far you can get with this.
must find the point or just what x equals for the extrema?
Can you find the point?
Yeah. Oh, wait. Actually, I don't think you can.
Why not?
Because it's plus c when you find the antiderivative,
Ah, okay.
so you wouldn't be able to know where it is.
Ah! Sorry. I used the smart board eraser on the regular board. I don't know what havoc this is about to wreak.